Hello, class. Welcome to the channel and welcome to the playlist in which we are discussing about some very special transforms which helps us to shift our signal from time domain to frequency domain and vice versa. We started our proceedings with Fourier series and then we learned about Fourier transform. We saw the basics of Fourier transform. We saw its properties. We saw few of its conditions which required to be satisfied in order to signal to be able to find a Fourier transform. We saw the Fourier transform for periodic signal, and we also saw the same for uh, saw few theorems which were about Fourier transform, which helped us discovering the Fourier transform of our signals. And in the last, we saw the inverse Fourier transform, and now we are dealing with Laplace transform, and we are taking the same path. We are discussing the about the Laplace transform from the base. So just like Fourier transform, now this time I want you to find the Laplace transforms. We already discussed about its properties in last lecture, so if you haven't checked out the last lecture yet, please click on the I button which will be flashing on the top right hand side corner of your screen. So um, please check that out if you haven't, because this video requires the knowledge of that video. If you have knowledge of Fourier transform basics and its properties, then it will be easier for you to grasp the concept. And that out of the way, let's get started. Let's start talking about the Laplace transform of my unit step signal. So basically I want you to be familiar with inverse Laplace transform, but in order to grasp that concept, you must know what is the Laplace transform of my unit step signal. So you can also see it as a numerical problem in which we want to find the value of Laplace transform of my u of t, which is my unit step signal. So here what we are doing, we are taking x of t is equals to u of t, which is my unit step signal, and basically we will apply the Laplace transform formula on it. So we are taking the Laplace transform formula, which means minus infinity to infinity. X of t is u of t, so we will take u of t e raised to minus st into dt. And as we are taking unit step signal, remember in unit step signal we always go from 0 to infinity, and all the values of my signal will remain 1 from 0 to infinity. So here what will happen, the integral will change, which was earlier from was going from minus infinity to infinity. This time it will only go from 0 to infinity, because every single time we consider a unit step signal, we take values for t greater than or equal to 0. So integral will change, and e raised to minus st into dt, because value of u of t, as I earlier said, the value of u of t will be 1. So we will be basically taking integration of e raised to minus st into dt. So what is the integration of e raised to minus st? Given that s is a constant value, so it will be e raised to minus st divided by minus s. In integration, we divide the constant, we our divide the constant, uh, we put the constant in the division of my actual integration. So we will get e raised to minus st divided by minus s. And when we substitute the limits were 0 to infinity. So when we substitute it, so we will get e raised to minus s into, instead of t, what you will do, you will substitute infinity. So you will get e raised to minus s into infinity, which basically is equal to e raised to infinity, and value of anything raised to infinity will be 0, so it will be 0 minus e raised to 0. So also you know what is the value of e raised to 0. E raised to 0's value will be 1. So basically in the numerator section you will have -1, and in the denominator you are already having -s. There is no need to do any changes in it. There is no variable multiplied with it, so it will remain -s. So now -1 upon -s, which means the value of my Laplace will become 1 by s. So the Laplace transform of my unit step signal will be 1 by s. And the special thing and the base reason why I wanted you to know the Laplace transform, why I wanted you to be familiar with numerical problems, is to find the ROC of your given signal. Okay, so whenever you are finding ROC, what you will take care of that your signal must remain absolute integratable signal, right? That was the primary condition for your signal to be a Laplace transform, for your Laplace transform of your signal to exist, besides of having a Fourier transform of my signal, right? And if you look into it, that is also the condition for my Fourier transform to exist as well. So what you can do, if the Laplace transform of your signal is 1 by s, then you have to make sure that what will be the value you can substitute in this formula, so that your Laplace transform will become 0, or sorry, not will become 0, your Laplace transform will become infinity, right? Because if you want to find the Laplace transform, then your signal must be finite. So if you put 0 instead of s, you will get 1 by s, which will be equal to 1 by 0, and 1 by 0 is infinity. So for that it will not be converted. So for the values less than s, less or equal to s, your Laplace transform will not be converged. So what you will do, your ROC will be s greater than 0. So you can find the ROC here, all the values greater than 0 of s, your Laplace transform will converge, and hence you can say that the Laplace transform of your unit step signal can be given as 1 by s, and its ROC will be s greater than 0 or your sigma greater than 0. Now let's come to the topic which I really wanted to discuss. It is inverse Laplace transform. So by the way, you have to recall little bit of partial fraction here, because I'm going to discuss it. So if you are not familiar with partial fraction, please go and follow old mathematics books, calculus books, algebra books, so that you will get a little bit better idea. So for any function of my Laplace transform, you can express any Laplace function in a partial fraction expression, right? And how you can express it? So you can express it using this formula. Your x of s is equals to k0 by s minus s0 plus k1 by s minus s2 plus k2 by s minus s2 plus up to it will go till n. Okay, so we can also find the Laplace transform of any equation using its using using its um, transform pairs. You can call them transform pairs. Like if you want to find the Laplace transform for L of u, you can directly find it, right? Sorry, u of t, you can directly find it. But now you want to find the Laplace transform of this function. Say you want to find the Laplace transform of this function e raised to at into u of t. So the Laplace transform of my e raised to at into u of t, because you already know what is the Laplace transform of u of t, the Laplace transform of u of t is s. Okay, and earlier when we saw the properties of Laplace transform, we saw that whenever we get anything whenever we get e raised to at in multiplication with my signal, my Laplace transform will become 1 upon s minus whatever multiple my time variant is having, right? So the term which is multiplied with t is a, so we will get 1 upon s minus a, right? Now again, to find the region of convergence, what you will do perform the same exercise. So in order to make it infinity, your s should be equal to a, right? Your s should be equal to a. So what you will do, you will make sure that that thing will not happen, because if such thing happens, then your Laplace transform will not converge. So in order to make your Laplace transform converge, what you have to do, you have to take all the value of s greater than a in your ROC, right? So your region of convergence will become all the value of s greater than a, and based on this value 1 upon s minus a, you can also find you can also find the time domain function related to this, right? Initially we went from time domain to frequency domain. The time domain was e raised to at u of t, and we went from time domain to frequency domain, and what did we found 1 upon s minus a. Now from 1 upon s minus a, we can find back the value of minus e raised to at u of t again, right? Or you can also find minus e raised to at u of minus t. Whenever your signal will converge for values in the inner circle, like or in the left hand side of your pole, at that time you will have minus component associated with your uh, main time variable, right? So always remember that. So the two different signals can have same Laplace transform, but uh, but at the same time they might not have the same ROCs, because if they will have same ROCs, then basically they are the same signals. So you can see the same for both of the signals. So the one on the left hand side is for the first term, which we found the Laplace of, uh, the one which was called e raised to at u of t, and for that the ROC was s greater than a. So here you can see, for this is your a, this is your pole a, and all the values of s greater than a, your Laplace transform converges, and you have shown it using this dotted checkered things. Okay. So the ROC is as greater than a on the left hand side image, and now for the right hand side image, as you can see that the region of convergence is on the right hand side of my pole, right? Or you can say, as per they have written, that ROC of my signal, uh, the pole will lie on the left hand side of ROC, right? Both the things are true. And for the other one, in which the region of convergence was s less than a, your pole is lying on the right hand side of your ROC, right? So that is the difference. Whenever your pole lies on the left hand side of your ROC, the time domain signal is right sided, right? Always remember, again come back here and see, whenever your pole will lie on the left side of your ROC, like your pole is here and here is your ROC, which means the pole is lying on the left side of ROC. That means the time domain signal is on the right hand side, right? So you can see that time domain signal in this case will be on the right hand side, this formula. And whenever the pole will lie on the right hand side of your ROC, as you can see, your pole is lying right hand side of your ROC. In such cases, the time domain signal will be left sided. So here you can see the time domain signal on the left side, right? And by the way, they have shown dual way arrows, which means you can find the Laplace from time domain and time domain to Laplace. You can shift both ways. So whenever I'm saying that your time domain signal is on the left hand side, or your time domain signal is on the right hand side, both of them will be true in this formula, because they have written this formula that way. Okay, if you want to write it another way, you can count that way as well. And again, if the ROC will be totally right hand sided, right, then your time domain signal will, due to all the poles, will be right hand sided. Okay, so if ROC is totally right sided, then time domain signals due to all poles will also be right sided. And same ways, if your ROC is totally left sided, then the time domain signals due to all the poles will also be left sided. Okay, so whenever you find the Laplace transform of anything, consider these things in your mind. So these things can help you find the Laplace transform very easily and identify either it is a Laplace or inverse Laplace transform. Now you can also find the inverse Laplace transform with the help of convolution. And we already know convolution is now we are already one of the famous and favorite topics. So think about it, that you are having a signal x of t or x1 of t, two signals you are having, x1 of t and x2 of t, and respectively their Laplace transform is x1 of s and x2 of s. Okay, and uh, if you take convolution of both of them and then take the Laplace transform of it, so what you are doing, see this formula, you are taking convolution x1 of t convolved with x2 of t, and you are taking Laplace of the whole term. So the output you will be getting will be same as x1 of s into x2 of s, right? So same ways as you can represent the function fs as a product of f1s and f2s, what you can do, you can represent your x of s as the product of x1s into x2s. And you can try to prove the reverse as well. You can take the inverse Laplace transform of this, you can take the inverse Laplace transform of x of s. So what you will get, you will basically put this value here, x1 of s into x2 of s. So what is x1 of s into x2 of s? So basically they are x1 of t in convolution with x2 of t, right? So that is also truth. So that works both sided. Convolution theorem works both sided. You can find convolution if you can take the Laplace transform of two signals who convolve with each other. The output will also be same as the multiplication of both of these signals in the Laplace domain or frequency domain, whatever domain you want to call it. And if you take the inverse, then again you will find the same output. And basically in the last they have just written the formula of my convolution theorem, so nothing to worry about. We have seen that thousands of time now. So that was the inverse Laplace transform using convolution integral. Now let's move and let's see the Laplace transform for network analysis, which is very much important from the perspective of signal processing engineer. So before we move to the network analysis and uh, different type of circuit elements, I I have to tell you that you can find the uh, you can do the analysis of your network, but for that the initial conditions are very important, right? You must have studied initial conditions in the circuit and network class, because you are taking this course in the fifth semester at least, so you might have knowledge about uh, your circuit parameters and initial value. But still, I will give you a small hint. You can take the unilateral Laplace transform in order to solve the differential equation with linear conditions, and you can find the Laplace transform using this differential conditions. Now that's out the way, let's talk about the Laplace transform of my network analysis. The first one will be the resistor, and as expected, as you all expect from resistor, it will be pretty much simple. So you can easily use Laplace transform for all the network analysis and all type of network components like resistor, inductor, capacitor, all type of components. And uh, first, let's take this circuit. As you can see, it's a simple circuit. We are having voltage across this signal circuit as Vs. For initially, when it will be in the time domain, its voltage will be Vt, right? And the current flowing through it will be It. As you can see here, it will be It, and the value of resistance will be R. So you can give the formula for voltage in the time domain with this formula: V of t is equals to R I of t. Now because we know that my voltage and my current both are functions of time, and basically R is constant because it is resistance, so you can find the Laplace transform of this equation, and the Laplace transform will look like this. Your voltage in the time domain will become voltage in the frequency domain. Same thing will happen with current, and you will be able to express your equation after in the frequency domain as this equation: V of s is equals to R into I of s, right? And you can use this circuit, this final circuit, in the Laplace domain or frequency domain. Now let's see the second component, the interesting one, the inductor. So basically we are discussing about the single elements only. We are not talking about their series, parallel or cascaded connections. We are talking about individual component only. So now let's consider the single inductor, and we already know what will be the value of voltage across my inductor. You can give the value of voltage across your inductor using this formula: V of t is equals to L di by dt. Nothing new here, we all know the formula. Now what we will do, in order to shift my signal, because see, initially this signal is in the time domain, you want to shift it in the frequency domain. So in order to shift this signal in the frequency domain, what you will do, you will take the Laplace transform. So by taking Laplace transform, what you will get, your V of t is equals to L di by dt. So whenever you will take Laplace transform, you will get this time domain signal of voltage will come in the frequency domain. So you will have V of s is equals to, now what will be the value of Laplace transform of L di by dt. So L is a constant, so it will be thrown out, and instead of I, what will happen, you will get s into is minus I into 0 minus. Remember, I've told you to learn about the initial conditions. Revise it. How? Because di by dt, dit of t by dt will be this: s into is minus I of 0 minus, right? So that is the this one is the formula for a Fourier transform, and this is the result of your initial conditions. Initially we are taking I of 0. So you can write your final voltage equation in the frequency domain as this: V of s is equals to S L I of s minus L I of 0. And you can represent the equivalent circuit which prepared from this equation, as you can see the circuit in the middle. Okay, uh, not actually the circuit in the middle, actually it is a different circuit. Wait a minute, I will show you. So it will be same as this circuit which you are seeing on the left hand side, but instead of capacitor you will have your inductor, and the current will be is, and the value of inductor will be sl. So come here back and see the first image. In the first image you can see the product of initial current and inductance is L into I 0 will form the voltage source, as you can see in this first image here. This V of 0 was forming voltage source, so here we will have L into I 0 we will be which will be forming my voltage source, and the inductor will become S into L in the Laplace domain. Okay, initially the inductor was L and voltage was V of t, current was I. So by rearranging this formula you can also find the formula for current. So uh, I am asking you to mention what will be the formula of current in the comment section. You don't have to do anything, you just need to rearrange this formula in order to find the formula of current. You need to make is the subject, and that would be it. Please mention that mention down the value of is in the comment section below. And do write that it will be the Laplace transform of a single inductor, because I'm going to ask the same for capacitor as well. Again, based on uh, equations, you will be need to find it. And as we have obtained two equivalent Laplace transform circuits for inductor, we can use KVL and KCL in both of them, and our final circuit will look like this. So remember I told you current will be L into IO, right? So it will be here. Your inductor is showing 1 by SL, your current is I of S, and your voltage is V of S. Now let's see the same for my capacitor. So here you are having the Laplace transform for single capacitor. So again we all know what is the voltage value across the capacitor. It can be given as this formula: V of t is equals to 1 by C integration 0 to t it into dt plus V of 0 minus. So same as we did for the Laplace transform of single inductor, we will take the Laplace transform again here, and I will convert this equation which is in the time domain into the frequency domain equation. So we will have V of s is equals to 1 by c. 1 by c will remain as it is because 1 by c was nothing but a constant. This it into dt will become is divided by s, and this v0 will become v0 divided by s. Okay, so that will be the voltage formula. You are getting s in the division of v0 as well. Don't mess the math up. Please revise the initial conditions. I'm not going to explain the whole topic in here, but you can revise it. So based on this equation we can prepare the Laplace circuit again, and the initial circuit was this. In the time domain we were having V of t as my voltage, I of t as my current, and capacitance as C. And in the Laplace transform, or in the Laplace or frequency domain, you will have this as your circuit. So you can see that in that circuit what is happening: the initial charge on the capacitor will form voltage source, which can be given as this formula: V0 divided by S. The impedance of the capacitor will become 1 by SC. which was c in time domain, and your current can be represented will be represented as I of s, and voltage will become V of s. So you can again rearrange the equation, which equation, this equation, and find the value of current in the frequency domain for the single capacitor. So again I'm asking you to mention that as well in the comment section. The first users we will answer this will get a shout out. So do mention them, and let's see who gets the right answer first. You just basically have to rearrange it, there's nothing new in here. Okay, and based on the above equation, a new equivalent circuit can be drawn like this. In this new equivalent circuit, your capacitor will be SC, it will be in parallel with your current source, and your current value will be I of S, voltage's value will be V of S. So these were the Laplace transform for your network analysis. Basically we took all three basic network components: resistor, inductance and capacitor. Now let's move forward to the next topic, which is the relation between Fourier and Laplace transform. So to those who already saw this coming, are the ones who are paying the most attention in the class, because I already mentioned about this thing earlier in the class as well, that your Laplace transform has a huge resemblance with Fourier transform, and now we are going to see how both of them are related. So we all know that in Fourier transform the value of S is sigma plus j omega, because we basically Laplace transform is in Laplace transform the value of S is equals to sigma plus j omega, and we all know basically Laplace transform is a transform in the Fourier in a transform in the frequency domain. So can't we write the basic equation of Laplace transform, which was x of s is equals to minus infinity to infinity integration x of t into e raised to minus st into dt, as this equation, right? So in this equation we are not doing anything new. Instead of s we are just replacing its value, which is sigma plus j omega. So we will get integration minus infinity to infinity x of t e raised to minus sigma plus j omega of t into dt, right? And why are we doing this? So that we can find the relation between Laplace and Fourier. So what we will do, we will separate this bracket out. So we will get separate values of e raised to minus sigma t and e raised to minus j omega t. And whenever we get that, let's put these two terms in a bracket together. So here you can see we put two of these terms in the bracket together. So here you are having in the bracket x of t e raised to minus sigma t in the bracket, and it is integrated over minus infinity to infinity with e raised to minus j omega t into dt. But if I call this term, which is in the curly bracket, as x of tau, and then see this formula, it is the same formula as the Fourier transforms formula. Basically it is the formula of Fourier transform, right? So Laplace transform is nothing else but actually a Fourier transform of this term x of t into e raised to minus delta t, minus sigma t. So if I take s is equals to j omega, what does it means? It will mean that the value of your sigma is 0, right? And when such thing happens, what will happen here? Whenever you take your sigma is equals to 0, at that time whenever you take Laplace transform of it, the equation will look like this: x of s is equals to minus infinity to infinity x of t e raised to minus j omega t into dt, right? Which means whenever you take your sigma equals to 0, your Laplace transform basically becomes your Fourier transform, right? Because you are what value you are getting, x of s is equals to x of j omega, which means x of s and x of j omega is equal, which means s is equals to j omega, right? So whenever you take sigma equals to 0, your s becomes j omega, which means if you take the value of sigma equals to 0, then your Laplace transform and Fourier transform becomes equal, same, identical. So that was the relation between your Fourier transform and Laplace transform. And from now on the lectures we will be from upcoming in the upcoming lectures we will be discussing the DTFT and DFT, discrete time Fourier transform, and we are also planning to discuss about FFT as well, the fast Fourier transform. So uh, again I'm telling you, if you haven't revised the initial conditions, do revise it. If you are unaware of the basics of signals, please check out the playlist. The initial playlist we discussed about all types of signals, so that you can understand the upcoming lectures very well. If you have any doubts related to today's class or any previous classes, feel free to mention your doubts in the comment section below. I will try to answer all your doubts as soon as I can. And again, that's it from today's lecture. So thank you very much for listening. I will be seeing you in the next lecture. Till then, goodbye and take care of yourselves.